Good day to all of you. Welcome to Learn Physics with Jasnov. No more hard feeling towards physics. In today's session, we will be discussing about the introduction part of Electrostatics, Unit 1 of Class 12 Physics. In today's session, I would like to discuss frictional electricity, properties of electric charges, Coulomb's law in vector form, units of charge, relative permittivity or dielectric constant, and continuous charge distribution. There are three types of continuous charge distribution: linear charge density, surface charge density, and volume charge density. The first topic is frictional electricity. It is not a new concept for class 12 students because the basics of frictional electricity you have studied in junior classes. There was one very classic activity you all might have done in some of our junior classes, like taking a plastic roller and rub against your hair, which has to be very dry, and after rubbing it for a few minutes, if you keep the roller next to small bits of paper, you all might have wondered that time, seeing that the small bits of paper are getting attracted towards the plastic roller. It is because of frictional electricity developed in the plastic roller. Let us look into what is frictional electricity. It is nothing but the electricity produced by rubbing two suitable bodies and transfer of electrons from one body to another body. As we all know, in chemistry, you all might have studied that every body is made up of atoms, and the most important charged subatomic particles are electrons and protons. Electrons are negatively charged and protons are positively charged. When a body is losing electrons, it becomes a positively charged object, and if a body is gaining electron, that develops a negative charge. Now, let us look into frictional electricity produced when two objects are rubbed against each other. Let us take the example of a glass rod and a silk cloth. When you are rubbing a silk cloth over the glass rod, you can observe that glass rod will be having positive charge and silk cloth will develop negative charge. As I told you, for positive charge to be formed, the object has to lose electrons, and for negative charge has to be gained, the object should gain electron. Now, when you compare the materials glass and silk, the electrons in glass are loosely bound as compared to electrons in silk. So when you are rubbing glass rod against a silk cloth, the loosely bound electrons will be easily transferred to the silk cloth. As a result, glass rod will become positively charged and silk cloth will become negatively charged. One point to be noted here is the number of positive ions gained by glass will be equal to the number of electrons, the number of negative signs which I have drawn on the silk cloth, which means as many numbers of electrons are lost by the glass, those only could be gained by silk. Okay, let us look into another example, another pair of materials. It is an ebonite rod and a fur. When a fur is rubbed against ebonite rod, after rubbing, you can see that ebonite will develop a negative charge and fur will develop positive charge. So what do you conclude from here? That when you compare the materials ebonite and fur, ebonite is having strongly bound electrons than the fur. So during the rubbing, loosely bound electrons from fur will be transferred to the ebonite rod, and after the rubbing procedure, ebonite will receive as many electrons as it has been lost by the fur. So number of total negative charge gained by the ebonite rod will be equal to the number of electrons lost by flannel. So this kind of production of electricity due to the transfer of electrons from one body to another body is known as frictional electricity. This is the basic of electrostatics. As in this unit, we will be discussing about the behavior of static charges. That is, what happens or how will the charge behave when charges are kept at rest. We have already discussed these points, that it is very important to note that electrification of the body is due to the transfer of electrons. If electrons are transferred from a body, then the deficiency of electrons makes the body positive, or if the electrons are gained by the body, then the excess of electrons makes the body negative. All these points you might have studied already in chemistry. Let us look into properties of one of our physical quantity which we will be discussing in this unit is charge. Charge is a physical quantity, which means it can be measured, it can be expressed in terms of a number. Let us look into what are the properties of charges. As we all know that there exist only two types of charges, namely positive and negative charge. Second property is like charges will always repel each other and unlike charges will always attract each other. The force will be repulsive if the two charges are of like nature. That is, if one positive and another positive charge is kept nearby, their interaction will result in repulsion. On the other hand, if one positive and one negative is kept nearby, their interaction will result in attraction of the two charges. The same thing will happen if two negative charges are kept nearby. They are also of like nature, so they will result in a repulsion of these two charges. Third property is charge is a scalar quantity. Scalar means what? It do not have any direction. It do have magnitude, but direction is not required for the description of charge. Fourth property is charge is additive in nature. As suppose you are having an object. Inside the object, if there are three charges placed at different locations, in order to find out the total charge enclosed within that body, regardless of the position of the charges, you can just add the three charges. For example, I have shown here an example of three charges, plus 2, plus 5 and minus 3. So the net charge enclosed within the surface will be plus 4 coulomb. It does not depend on the position of the charges. Charge is additive in nature. Fifth property is charge is quantized. About quantization of charge, you all might have studied in class 10th physics. I'll tell you once again what is quantization of charge. As we know that electron is the smallest charge which is present, and electric charge exist in discrete packets, which means every object can have a charge which is integral multiple of electronic charge. As everybody know that the charge of one electron is 1.6 into 10 raised to minus 19 coulomb. So any charge is possible if it is integral multiple of electronic charge, which means there can be a possible charge which is 100 times than that of electronic charge, or 12 times than that of an electronic charge. But you cannot practically find any body which carries 2.3 times electronic charge or 19.6 times electronic charge. That is not possible. All the practically possible charges has to be integral multiple of electronic charge. That property is known as quantization of charge. Let us look into the next property of electric charge. It is conservation of charge. When we discussed about rubbing of materials, I have told you to note down one point, that the positive charge and the negative charge magnitudes has to be equal. That is, when I took glass rod and silk cloth before rubbing, both of them were neutral, which means the total charge before rubbing was 0. And after rubbing, suppose the glass rod developed plus 10 charge, and the silk cloth developed minus 10 charges, the total charge after rubbing also remains the same as 0. That is called conservation of charge. That is, the algebraic sum of positive and negative charges in an isolated system should always remain constant. That is known as conservation of charge. Now, there is one more property that it does not change with velocity. See, in class 11th, we have studied most properties of mass. One of the property of mass is mass according to Einstein's special theory of relativity. When an object of mass m is moving with a velocity which is comparable to that of the velocity of light, its mass will change. Rest mass and amount of mass at motion are different. But contradicting to that, charge do not change with velocity. So these are the important properties of electric charge. I hope it is very clear to all of you that there exist only two types of charges. It can have repulsive or attractive force based on the nature of the charges. Charge is a scalar quantity. It is additive in nature. Charge is quantized. It is conserved, and it do not change with velocity. Now, there is one point I would like you to note down. While discussing about quantization of charge, I told you that electronic charge is considered to be the fundamental charge. But recent studies have shown the existence of another charged particle, which is called quarks, which may have a non-integer value of electronic charge, that is 1 by 3e or 2 by 3e. These are the two postulated quarks particles. Now, if these quarks are detected, then also there won't be any change in quantization law, where we'll just change the quantization of, instead of electronic charge, we should write quantization of charge as charge will be integral multiple of quarks. Okay. The next topic of ours is Coulomb's law, which is one of the very fundamental law in electrostatics, which regulates the force between 2-point electric charges. Let us consider 2-point charges, say Q1 and Q2, which is located at a distance r from each other. Then, according to the statement of Coulomb's law, it states that when these two charges are placed at a distance r, it can have a force of attraction or repulsion, and the magnitude of force will be directly proportional to the product of the charges and inversely proportional to the square of the distance between them. That is, mathematical formula for Coulomb's law can be obtained from the statement itself. As the statement says, F is proportional to product of the charges. We have taken Q1 and Q2 as the charges. So we can write F proportional to Q1, Q2, and it is inversely proportional to square of the distance, which means if distance we have taken as R, then you can write F proportional to 1 by R square. Combining these two, you can write F proportional to Q1, Q2 by R square. As we have studied in physics, to solve the problems, we need to develop an equation, which means the proportionality has to be replaced with an equal to symbol. At that time, one constant of proportionality has to be introduced. So here, the constant of proportionality is K. It is a positive constant, and its name is electrostatic force constant, or Coulomb's constant. The value of K in vacuum is 1 by 4 pi epsilon naught, where epsilon naught is called the permittivity of free space. It is one exclusive property of free space. In a medium, suppose other than vacuum, we are keeping the two charges in a different medium, then the value of constant K becomes 1 by 4 pi epsilon. Instead of epsilon 0, we will be using the term 1 by 4 pi epsilon, where epsilon is called absolute electric permittivity of the dielectric medium. The dielectric constant or relative permittivity can be calculated by using the formula K equal to relative permittivity, that is permittivity of the medium relative to the free space. So mathematically you can write epsilon r equal to epsilon divided by epsilon naught. So for force in vacuum, the formula can be 1 by 4 pi epsilon 0 q1 q2 by r square, whereas in medium the formula becomes 1 by 4 pi epsilon 0 epsilon r, because by using this formula epsilon is equal to epsilon 0 into epsilon r. So epsilon 0 epsilon r q1 q2 by r square. Epsilon 0 value is 8.8542 into 10 raised to minus 12. Its unit will be Coulomb square per Newton per meter square. And value of 1 by 4 pi epsilon 0 is equal to 8.9875 into 10 raised to 9. But while solving the problems, this value can be taken very close value is 9. So while solving the problems, the value of 1 by 4 pi epsilon 0 can be taken as 9 into 10 raised to 9. Its unit will be Newton meter square per Coulomb square. This is the statement and mathematical formulation of Coulomb's law. Now, Coulomb's law in vector form, because we know that force is a vector quantity. It do have magnitude as well as direction. Magnitude of force we have already discussed. It can be found out by using the formula K Q1 Q2 by R square. Whereas whereas the direction of force depends on the nature of charges. Now, I'm showing you the example of two positive charges, plus Q1 and plus Q2, which means product of the two charges will be greater than 0. If R is the separation between Q1 and Q2 and R12 represent unit vector along the direction of R, there will be two forces acting. One, I'm naming it as F12, which means force at 1 due to the presence of second charge. That force acting at Q1 due to the presence of second charge. And second force will be F21, which denotes force at Q2 because of the presence of Q1. Magnitude of these two forces will remain same. Now I'm going to show you another example where also the product of charges are going to be greater than 0. How is that possible? I'm going to take two negative charges. One is minus Q1, another one is minus Q2. Here also the direction of force will be same. That is, if two charges are like charges, then the direction of force will be away from the charges. As you can see here, the direction of F12 will be away from Q1, direction of F21 will be away from Q2. Here also the direction of force remains the same even though we have taken minus charges. So if both the charges are like charges, whether it is a pair of positive charge or a pair of negative charge, the direction of force will be away from the charges. That is, you can write down the formula as F12 equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square into unit vector R21, because the direction of unit vector R12 is from left to right, but our force is acting in the opposite direction, so you will be writing unit vector R21. And for F21, you will write 1 by 4 pi epsilon 0 Q1 Q2 by R square unit vector R12, because the direction of F21 is from left to right and direction of unit vector R12 is also from left to right. In the second case, I'm going to take two unlike charges. That is, if one charge is positive and another charge is negative. In that case, we can say that the product of charges will be less than 0 because one is positive, another one is negative. When you multiply a positive and negative number, you will be getting a negative number. Position is R, position vector, unit vector is R12. Here also there will be two forces, but these forces will be acting towards the charges. As you can see, force at 1 due to the second charge will be acting towards the second charge. Force at 2 due to the first charge will be acting towards the first charge. So when two like charges are interacting, the direction of the force will be away from the charge, and when two unlike charges are interacting, the direction of force will be towards the charge. Now, for F12, the direction is along the direction of R12. Therefore, unit vector you can mention R12, whereas F21, the direction will be in the direction of unit vector. This is about the direction of force in Coulomb's law. So magnitude of force can be found out by using the formula 1 by 4 pi epsilon 0 q1 q2 by r square. Direction of force can be marked by looking at the nature of two charges. If both the charges are like charges, force will be acting away from the charge, whereas if both the charges are unlike charges, force will be acting towards the charge. So this is all about Coulomb's law and the direction of two vectors. As you can see, both the forces will be having the same magnitude, only direction will be changing. So F12 will be equal to minus F21. And when you write in vector form, if you change the unit vector into position vector R12, as we have studied in class 11, unit vector can be written as position vector divided by magnitude of the vector. So the cube in the denominator is coming just because we are taking the vector form, but otherwise Coulomb's law obeys inverse square law only because force is inversely proportional to square of the distance. Now let us look into what are the units of electric charge. The SI unit of electric charge is Coulomb. We'll be using the symbol C to represent it. 1 Coulomb of charge can be defined from the equation of force. We have studied F is equal to 9 into 10 raised to 9 into Q1 Q2 divided by R square. In this formula, if you substitute Q1 and Q2 as 1 and R as 1 meter, you will be getting the answer of force as 9 into 10 raised to 9 Newton. So when you make this into a meaningful sentence, it becomes the SI definition of SI unit of charge. That is, 1 coulomb of charge can be defined as that charge which when placed at rest in vacuum at a distance of 1 meter from an equal and similar stationary charge, because we have taken Q1 as 1 coulomb and Q2 is also 1 coulomb, distance as 1 meter, then they will repel each other with the force which is 9 into 10 raised to 9 Newton. This is how the definition of definition of 1 coulomb can be done. Now, in CGS system, the unit of charge is stat coulomb or SU of charge. In CGS system, the value of K is 1. Therefore, Coulomb's law equation becomes F is equal to K. K means 1 only. So, F will be equal to Q1 Q2 by R square because the value of K is 1 in CGS system. Now, in CGS system, definition of Coulomb can be if Q1 equal to Q2 equal to 1 coulomb and R equal to 1 centimeter, then force will be equal to 1 dyne. So charge will be called as stat coulomb there. It is plus or minus 1 stat coulomb. Relative permittivity or dielectric constant or specific inductive capacity or dielectric coefficient. All these are the names given to just one quantity. It is the relative permittivity. We have already studied in the previous slide that epsilon r is equal to epsilon by epsilon 0. This epsilon r has got another names as relative permittivity, relative permittivity or dielectric constant or specific inductive capacity or dielectric coefficient. Out of this, dielectric constant and relative permittivity are the most commonly used terms. Continuous charge distribution. As I told you in the beginning, there are three types of continuous charge distribution. One is linear charge density, another one is surface charge density, and third one is volume charge density. That is, instead of having discrete charge, if a charge is distributed over the surface of a conductor, linear charge density will play an important role if the shape of the conductor is in such a way that its length is so big as compared to its breadth and thickness. Suppose you are having a wire which is given a positive charge, then the charge is distributed over a straight line. Or we can say that if the charge is distributed over the circumference of a circle, or if the charge is distributed over the edge of a cube, in all these cases, we will use the term linear charge distribution, and it can be defined as the charge per unit length. Lambda is a symbol given for linear charge density. It will be equal to Q by L, or if you take an infinitesimally small charge dq over a very small length dl, we can write lambda is equal to dq by dl. Since we know that the SI unit of Q is Coulomb and SI unit of L is meter, the SI unit of lambda will be Coulomb per meter. Second one is surface charge density. It is represented by using the symbol sigma. Surface charge density will play an important role when the charge is distributed over a surface. That is, if the shape of the conductor is in such a way that its thickness is very small as compared to its length and breadth. That is, it will be having a considerable length, a considerable breadth also, but its thickness will be very small. In that case, charge will be distributed over an entire area. And surface charge density can be defined as the charge per unit area. That is, sigma is a symbol given to it. And if you have taken a small surface area ds, and if dq represent the charge of that small area ds, sigma can be written as q by s, that is total charge by total area, or it can be written as dq by ds. So in order to get the total charge, we can cross multiply so that dq becomes sigma into ds. So total charge can be found out by integrating the expression, that is q equal to surface integral sigma ds. Let us look into the third one. Before that, the SI unit of surface charge density will be, as you know, unit of Q is Coulomb and unit of area is meter square. So SI unit of surface charge density will be Coulomb per meter square. Let us look into the third one, volume charge density. We use the symbol rho to represent it. This will comes into play when a conductor is having considerable length, breadth, and thickness. If dq is a charge enclosed over a small volume dv, by definition of volume charge density, it is the charge per unit volume. Rho equal to q by v, or you can write for small charge, rho equal to q dq by dv. So to get the total charge, dq equal to rho dv, therefore total charge will be q equal to volume integral rho dv. As you know, the unit of charge is Coulomb and unit of volume is meter cube. The SI unit of rho will be Coulomb per meter cube. So today we have discussed about frictional electricity, properties of electric charge, Coulomb's law, statement, mathematical expression, direction of Coulomb's law, and surface charge densities. I hope today's topics are very clear to all of you. We will be meeting with the coming topic in the forthcoming day. Thank you all of you. Keep watching and keep supporting.